If we allow ourselves to think about a curve as a collection of straight lines, like that, tiny ones stacked end to end, then we can think about the length of that curve as being the sum of the lengths of all the straight lines. And it might be helpful to figure out an expression for the length of an arbitrary tiny straight line along our curve. We could say that its x-axis distance from one end to the other is delta x, and that its y-axis distance from one end to the other is delta y. It would follow from the Pythagorean theorem that our tiny length is equal to the square root of delta x squared plus delta y squared. But there's another way of thinking about delta y. It could be the rate of change of the function f prime of x times the x-axis distance, delta x. Then our tiny length becomes the square root of delta x squared plus f prime of x delta x squared. Then if you do some algebra, like factoring out a delta x out of the expression inside the root, and then pulling it out of the root by taking its square root, you wind up with the square root of 1 plus f prime of x squared times delta x. As I mentioned, the plan would be to add all of these together. That's that one, 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 from one end of our curve to the other. So that would involve taking a summation. We could say that the arc length, usually denoted s, is a summation of sorts of square roots of 1 plus f prime of x's squared times delta x's. And that is how we arrive at the generalized formula for the arc length. Pardon me, I've changed the notation in the formula I've written here, and that's because I've stated this problem as a curve in terms of y. dy dx and f prime of x are the same. Let's take a stab at using this formula to calculate this arc length. So since the formula calls for dy dx squared inside of a square root that itself is having the integral taken, we may want to think about calculating dy dx separately before plugging it into this formula. So if y equals x to the fourth over 8 plus 1 over 4x squared, to take the derivative, I might want to make it easier on myself and express it 1/8 x to the fourth plus 1/4 x to the negative 2. That makes it easier to use the power rule. This means that dy dx will be 4 over 8 x cubed minus 2 over 4 x to the negative 3, which simplifies to 1/2 x cubed minus 1/2 x negative cubed. Re-express this before plugging it in there. I could factor out a 1/2, leaving x cubed minus x to the negative cubed, and I could say that that's also 1/2 x cubed minus 1 over x cubed. I could express this as a single fraction by unifying the denominators. So let's do that. Common denominator should be x cubed, so we're going to multiply this by x cubed over x cubed and get an expression 1/2 x to the sixth minus 1 over x cubed. Or equivalently, x to the sixth minus 1 over 2x cubed. That's some of the work out of the way, but the formula calls for dy dx squared. So maybe I could get that out of this again before plugging this whole expression into the square root. dy dx squared should be equal to x to the sixth minus 1 over 2x cubed squared. We're going to have to do some work on that. We could express it as x to the sixth minus 1 squared over 4 x to the 6. And I guess we'd have to FOIL out the top. Probably have to do it eventually, so I might as well do it now. That'll get us x to the 12th minus 2 x to the 6 plus 1 over 4x to the 6. I think that's as good as I better make it now before plugging in. So let's see what happens. Our integral will be from 1 to 2, like the problem stated, of the square root of 1 plus x to the 12th minus 2x to the 6th plus 1 over 4x to the 6th dx. So here we're in another situation where we could maybe make things better looking by doing common denominators again. So similar to the situation we were just in, we could have multiplying 1 by 4x6 over 4x6, 4x6 plus x to the 12 minus 2x6 plus 1 over 4x to the 6. Now that over 4x to the 6, you mustn't forget, is underneath a square root, which means it's like having a factor of 1 over square root of 4, which means it's like having a factor of 1/2 on the entire integral. Meanwhile, collecting like terms up here leaves us with another step in the right direction, hopefully, of x to the 12 plus 2x to the 6 plus 1 over x to the 6 dx. Now, that guy, let me move things up here. That guy, I think I could make a little bit better looking still by sort of individually treating these as having a denominator of x to the 6. So I'll have the square root of x to the 6 plus 2 plus 1 over x to the 6 dx. And now here comes one of the things about these surface area problems. This here, this pattern with the x to the 6 and a 1 over x to the 6 is very typical of something called the binomial theorem, the binomial square theorem, which says that something of the form a squared plus 2ab plus b squared can be factored into a plus b, a plus b. It's not the whole binomial theorem, but it's part of it. It's the part of it we need to be concerned about. If you think about it, that integral underneath there could be expressed, or actually the polynomial underneath the square root could be expressed as x to the 3rd squared plus 2 x to the 3rd 1 over x to the 3rd plus 1 over x to the 3rd squared, which means it can be factored into x to the 3rd plus 1 over x to the 3rd times x to the 3rd plus 1 over x to the 3rd. That, of course, means it's this expression squared. So our integral finally becomes something really nice, no more square roots even, because it's the square root of x to the 3rd plus 1 over x to the 3rd squared. Now that means that we have nothing more than the integral, forgot a dx, the integral from 1 to 2 of x to the 3rd plus 1 over x to the 3rd dx. And this one is kind of trivial, probably, relative to the skills that we have at this point. But I'll do the rest of it. I'll write this as the integral of 1 to 2 x to the x cubed plus x to the negative 3 dx, and integrate term by term to get 1/2 x to the 4th over 4 minus 1/2 x to the negative 2 evaluated from 1 to 2. The definite integral evaluates to 2.0625, which will be the length of the curve that we started off with.